Welcome. As a preparation to discuss necessary conditions for subRiemannian geodesics, in this video I will present the notion of energy and explain that for curves parametrized by arc length, minimizing the energy gives the same minima as infimizing the length. We will then parameterize the space of curves with finite energy and rephrase the problem of minimization in terms of an important map called the endpoint map and its extended version. We will see that energy minimizers are necessarily critical points of the extended endpoint map. And for this reason, we shall calculate the differential of the endpoint map. Let's see. We want to discuss necessary conditions for geodesics with respect to subRiemannian distances, and we will restrict to the case of Lie groups. So we are going to have G, a connected Lie group. We are going to have delta, a subbundle of the tangent bundle that is left invariant. Subbundle, which we also call it polarization. And we are going to have a left invariant norm. Which we actually think is coming from a scalar product, okay? So on delta, coming from a scalar product. So what we want to do, we want to infimize the integral of the length of the norm of the speed of curves connecting two points, okay? So we will do we'll discuss two things. First is this length structure, and then we will discuss how to parameterize the curves, okay? Let's start with the length structure. So it turns out that it's not so convenient to infimize length. It's better to infimize something similar that is called energy. Okay. So let's discuss first the difference between length and energy for curves. Okay. So let gamma be a curve, say defined on 0, 1, value into our group, be a delta horizontal curve. What does it mean? This means that the derivative exists almost everywhere, and the function is the integral of its derivative. And the derivative is a linear combination of vector fields giving a frame for delta. So U M T X M at gamma T, where X1 and Xm are left invariant vector fields on G, giving a frame for delta. Then when we identify with the frame the norm on Rn, we have that the norm of the tangent vector is just the norm of the vector u1 um. So let's call it this u. So this is the norm of u, where this norm here is the norm at the identities, the left invariant norm that we extend. Okay, and this u So with u is a function, it's an integrable function from defined on 0, 1, valued in Rm. And what is the length? The length of gamma is just the integral between 0, 1 of ut in dt. Remember that curves can be reparametrized and the length stays the same. So a small note is that if we reparameterize and we can choose always a reparameterization by arc length, but I would really like to keep the domain of definition to be the interval 0, 1. So I cannot, unless the length is exactly 1, I cannot choose parameterization by arc length, but I can choose a multiple of arc length. So I can reparameterize by a multiple of arc length. So we have that. What is this multiple? This multiple is exactly the length of the curve. And if we parameterize in this way, then you see the integral of u, which is actually, of course, between 0 and 1, gives the length. But now this number is constant. So I can also integrate the square of this number, and it will still be finite. Okay? So the very small remark that in this case, in which case, I have that u is not only in L1, but it's also in L2. Okay? So, in other words, up to reparametrizing a curve, I can always assume that its control is an element in L2. Okay. What we understand, we understand that we could also now consider not only the L1 norm of the control, but also the L2 norm. So let me tell. We deduce that to infimize length, we might restrict to absolutely continuous curves whose derivatives are in L2. Okay, these maps are called elements of W12. Okay. Okay, first derivative is in the function is in L2 and the first derivative is in L2. Okay, but let me observe something more. If I take a function in a control in L2, then by the Cauchy-Schwarz or equivalently by Jensen inequality, this is a very simple exercise to check that we have that the L1 norm is less or equal than the L2 norm. Okay, here it's important the measure of the domain is 1. Okay, so we have this inequality. Okay, how do we read this inequality? We read that the L2 norm. Let's think that the function is the curve gamma is parameterized by arc length. But we understand that also this integral of the L2 norm of the speed is at least equal to the length. Moreover, the Cauchy-Schwarz-Jensen inequality tells us that you have equality when the function is constant. Okay, so when the function is parameterized by arc length, when the curve is parameterized by arc length, this is an equality. Let me stress this. So with equality, if norm of u is constant. What we understand is the following. So let's give a name to this L2 norm of the speed of a curve. So let's introduce the energy of a control. So the elements in L2 of 0, 1 value into Rm, they're called controls. And their energy is defined as, okay, energy of u is by definition the 1/2 of the integral of u squared. Okay, so in other words, this is the L2 norm of u divided by 2. So this norm is the norm on Rm that we fixed, and instead this is the L2 norm that's induced on functions. And the Cauchy-Schwarz inequality gives us that we have that the length of a curve gamma is always less or equal than square root, okay, there's twice the energy of its control. Where gamma dot is equal sum ui's xi's in gamma. All right. Now let's try to infimize. And I claim that there is no difference in infimizing the length or infimizing the energy. Okay? Of course, it's the same. Infimizing the energy or infimizing the square root of twice the energy, it gives the same minima. But this quantity is always greater than this quantity. But if the curve is parameterized by arc length, they are the same, or multiple of arc length. So now, what we understand that hence for geodesics that are parameterized by multiple of arc length, then are both minima for the length, this is the definition of geodesics, but also minima for the energy. Okay, And therefore, we will just minimize energy. Okay, good. Let's see why, how one can think of minimizing the energy. So now I'm going to discuss the subject of the endpoint map. Okay, so let's remember we are talking sub-Finsler, talking about a sub-Finsler Lie group. And now even if it's not necessary from the beginning, we will think that the norm comes from a scalar product. So then this object we will call it subRiemannian Lie group. Okay, so we have the scalar product, so we can fix an orthonormal frame x1 xn of for delta. All right, so let's consider now the space of controls. This is called the space of, to be precise, one should say L2 controls. The purpose for doing this is to parameterize all possible curves starting from a point. So we consider L2 function from 0, 1 to R2, Rm. And they are equipped with L2 norm. The L2 norm norm of u is equal to the integral 0, 1 sum of ui t square dt square root. This is for all u in omega. Now, we will see this as the derivative of curves for which we have the property that the derivative is in L2, okay? But I want to clarify that actually this is a one-to-one correspondence, okay? So let me first write a sentence. So the space of controls is in correspondence with delta horizontal curves with derivative in L2, okay? And in fact, for all u in omega, one considers the system of ODE. So what's the system? So the initial point is the identity of the group, okay? So in coordinates, this is as many equations as the dimension of the group. And the derivatives, again, is a system of n-dimensional n conditions, equal which vector? The vector that one obtains by left translating from the identity the vector ut. And this is for almost every t in 0, 1. Okay, one solves this system called gamma u, the solution. Now, if we have a curve gamma whose derivative is in L2, then this derivative is exactly gamma u after up to left translating, brought to the origin. This is the vector u, which is in L2. Okay. Now, why this system can be solved? Okay, this is a little bit of analysis. Let me just make a remark, but then we will go back later in the case of Carnot group. So the solution exists and is actually unique because one can apply, for example, a theorem of Kara-Theodori on ODEs. I will not explain how to use the theorem, but it's very simple. However, for Carnot groups, which are particular subRiemannian groups we will discuss later, for Carnot groups, the explanation will be extremely easy. The explanation of the existence and uniqueness will be much simpler. So, believe me for now that the solution exists. And let's call it gamma u. Let's introduce some terminology, even if I actually already start using it. Gamma u is the trajectory of u, and gamma u is the control of gamma u. Now, we define the following map. The endpoint map as, let's call it end, and it goes from the space of controls to the group that for every control assigns the trajectory at the final point. So this is final point of the trajectory. Okay, let's define one more map. We define the extended endpoint map as, so let's call it end tilde, from the space of controls in the product manifold G times R, and to every u you assign the final point, so it's the endpoint map, but also taking care of the energy. Of u. Okay. All right. Now let's remember what we discussed at the beginning about being equivalent, minimizing the energy and the length. Okay. So we rephrase the property of being a length minimizer for a curve parameterized by multiple of arc length as being the trajectory of a control U for which, let me write it big, so there exists no other control, so there is no control V in omega with the property that has the same endpoint. So maybe let's just write here for a curve, length curve parametric of a curve, say from 1 to a point P. If P is the endpoint of U, but also the endpoint of V, and V would be V, the energy would be smaller than the energy. Okay, so U, or better gamma, the curve gamma, so the trajectory of U is a length minimizer if and only if it is an energy minimizer. In other words, there exists no other V that, remember, when we consider controls, all these curves start from 1, but now we want other curves arriving at the same point, P, and what we say is that there exists no other control with less energy. Okay. Now, let's conclude something from this observation. So we remark, so if gamma U is an energy minimizer, then necessarily U is a critical point of the endpoint, the extended endpoint map. Why? Okay, first of all, believe me that for the moment that endpoint map is a smooth map. Okay, so if you had a critical, if instead you were not a critical point, so indeed by contradiction, if instead you, if instead you were a regular point for the extended endpoint map, then this map end would have a local right inverse. I'm using the inverse mapping theorem. Okay, so if you have omega G times R and you have the endpoint map, if you have a regular point, this means as a surjective differential. If as a surjective differential, then you can find a local inverse. So you can find a map, say F, for which this doing F and then end will give you the identity. But in particular, you can find, and it is where this is in the neighborhood of the image of U. But then this would tell you that you can find points arbitrarily close to the image of U. In particular, you can find with the same first coordinate G and with less energy. So, okay, this would give us, giving the existence of some V with image V to be the same endpoint of U, but with energy a little bit less than U for some epsilon. And this will be a contradiction. Okay? So if we have an energy minimizer, then necessarily the control of this curve is a critical point of the extended endpoint map. Now that we know the critical points of the extended endpoint map are important, let's calculate the differential. Let's start with the differential of the endpoint map. So, proposition, the differential of the endpoint map is given by this following formula. So the differential at a point U in the direction of V is the differential of the right translation at the identity times or evaluated at the vector that is given by the integral between 0 and 1 of the adjoint of gamma U times S V S ds. This is integrated. Okay, and where this gamma is the trajectory associated to the control U. Okay, let me give the proof of this proposition in the case of linear groups. Okay. Proof for linear groups. G is a subgroup of GLN. It makes it simpler because the multiplication is just matrix multiplication, so the multiplications are linear. So what is it that we need to prove? So if we want to calculate the differential at U, the direction of V, what we have to do, we have to consider the map evaluated at U plus epsilon V. What is the map? The map is you take the trajectory and you evaluate at 1. Now you have a curve depending on epsilon, and you take the derivative in epsilon equal to 0. So this is what we need to calculate. All right. So let's study a little bit what is this curve here. So let's remember what is the endpoint map. So recall that so the endpoint map satisfies that, so for example, gamma U at 0 is 1, and gamma dot at U and time t is the left translation, and I will just write it as matrix multiplication times the control. Okay, you can see this as the left translation, the differential of the left translation, because anyway it's a linear map applied to this vector. Okay, so for linear groups you write it this way, and now we have to consider gamma of U plus epsilon V, which is similar system equal gamma of U plus epsilon V times T times U T plus epsilon VT. So here there are some T that I'm not writing. Okay, now let's look at least for the moment at this system here, and let's take the derivative in epsilon. Because I would like to come up with a new linear system, a new ODE, and in such a way that both this map here and some similar map coming from here, from this formula, satisfy. Okay, so I take the derivative in epsilon. So what do I get is that d gamma u plus epsilon v divided by the epsilon in 0 is the 0 vector, and d over dt of d gamma u plus epsilon v over d epsilon satisfies the following: d gamma 1 plus epsilon v divided by d epsilon times u plus epsilon v plus gamma u plus epsilon v times epsilon, sometimes v. Okay, this is the system. So setting sigma to be the derivative of this map, gamma u plus epsilon v at epsilon equal to 0, which is, pay attention, this is a map is still a curve in t, right? And when we evaluate at 1, we will have the image of the end of the differential. Okay, so this is a map in t. It's a curve in t. Now, what we have that sigma satisfies, okay, sigma in 0 is 0, and sigma dot is equal to sigma times u. So this becomes sigma. Now this becomes 0, and now gamma u times v plus gamma times v. So sigma satisfies this this ODE system. Okay. Now we claim that the curve eta, define the integral from 0 to t of the adjoint of gamma u s vs ds, right translated on the right by gamma t, satisfies the same ODE. Okay, namely, what is the ODE? Okay, let's go to the slide. Let me copy the ODE. Okay, put it here. So what is the ODE? I write it now for eta. So eta 0 is equal to 0, and eta dot is equal to eta times u plus gamma times v. This is what we claim. Let me erase the system for sigma. Okay, now this is clear. Okay, for t equals 0, this becomes 0. So now this other one. Okay, so why this is true? Okay, let's take the derivative of the curve eta. So eta dot is equal, okay, so here I have the depends in t twice. Okay, it's a product. So let's do one derivative at a time. So the first time I take the derivative, the integral disappears, have adjoint of gamma s vs times gamma. It should be gamma u, but let me write gamma. Gamma is gamma of u. Okay. Of course, this is not s anymore, it's a t. Okay, and maybe I will not even write sometimes the depends on t plus, and then have the what's on the left, and gamma s v s ds to t And now I have to take the derivative of gamma, and that's gamma dot. Okay, now the adjoint in for matrices coincide with the conjugation. So this is equal to gamma v times gamma minus 1. Okay, let me write the dependence on t. Gamma t times vt times gamma t minus 1, and then I have one other gamma t here, gamma t, plus, okay, now what is this? This is the curve, except this part is missing. So let me write it as the curve eta t times gamma t minus 1. So I would kill this. And I wrote this part. And then I have gamma dot. Okay, what is gamma dot? Gamma dot is the right translation of the control. Okay, so now I have gamma t ut. Now you see that we can simplify, and what I have is that eta dot satisfies the ODE system. And therefore, what we conclude is that eta t coincide with sigma of t for all t, and for t equal 1 gives what wanted, namely the derivative in epsilon of these functions in epsilon equaled this value here. And we calculated the differential of the endpoint map. If you like the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel clicking below. Bye.